In this video, we are going to look at optimization problems. They're from 4.5. No, they're from chapter 3 in the textbook. I don't know why this says 4.5. That must be from another textbook. So this is the end of chapter 3, maybe like around 3.6. Maybe 3.7, something like that. Objectives: solve applications involving optimization, solve optimization problems given a function modeling cost, revenue, and profit, solve optimization problems involving geometry and geometric, I should say figures probably, shapes, something like that. So we're going to be applying the first derivative test to applied problems that are word problems. So let's look at guidelines for solving optimization problems. First, we need to understand the problem, read it carefully. Take your time, write notes. It's important usually to draw a diagram. Not always needed, but many times helpful, especially in geometric examples. Keep track of your units as part of this too. Introduce your notation. So name your variables based on the problem and appropriately identify them. With what we call let statements. And or by labeling them on your diagram. If you have a diagram, identify the objective function and any constraints. So the objective function here, what am I minimizing or maximizing? Optimizing, right? Are you looking for maximum volume, maximum area, minimum cost, maximum profit, something like that? Any constraints? This might be things like budget restraints or space restraints or material restraints or maybe time restraints, things like that. So, and then you're going to use the first derivative test. Constraint information may be implied, such as things like distances are positive, time is always positive. It may be implied for things like you don't want to have a negative profit because then you're losing money and you're going out of business, things like that. So you may only be considering a portion of the graph which is feasible for the context of your problem. and that context of your problem may not be explicit restriction setup. You may have to read into the problem in the context to say, oh yeah, in real life, I'm not going to have negative time, or I'm not going to have negative distance, or I'm not going to have negative production. I really don't want to have negative revenue or negative profit. I might, that's a bad situation, but I may not want to show that part of the graph. I may only be interested in the part of the graph where really I'm staying in business. So solve your opt your objective function by using your constraints. Rewrite your objective function so that it's the function of only one variable, and then differentiate with respect to that variable. So use your constraints to write your objective function with only one independent variable, and differentiate with respect to that independent variable. Unless the problem makes you differentiate implicitly. We'll talk about when that would happen, then solve the problem, right? So in this example, let's maximize profit, right? So a manufacturer determines profit, which is in dollars, and can be modeled based off of the number of units produced. Call this demand, and it's usually our X that's sold. So P of X is equal to 8X minus 1,000th X squared minus 10,000. Find the production level X that yields maximum profit. So P, capital P prime, capital P is profit, lowercase p is price. It's going to be important in this section that you pay attention to capitalization. That's part of our notation, and defining our terms and things as our variables. Lowercase letters and uppercase letters are going to be different than one another, and you need to be careful with that. So we're going to set this equal to 0 and solve. 0.002x is equal to 8. 2x is equal to 8,000. X is equal to 4,000. So let's go ahead and make a sign chart here. 4,000. We're restricted here to produce no less than 0 items. We can't have negative production. Really, we're going to be probably restricted here by our production to have an X value here that is going to not go below 0 for profit, but anyways, this is going to be a parabola that opens down. We start at negative 10,000 here, and we're going to come up, and that's just the cost of being in business there before we sell anything. That there's just startup cost associated, and that's why you start at a negative value. That's pretty normal. So we're going to be increasing on this side. If I would test, for instance, P prime of, say, 1, P prime of 1 is going to be 8 minus 0.002. It's going to be 7.008, which is greater than 0. So this is increasing on this side. If I have P prime of, say, 4,001, that's going to be less than 0. It's going to be decreasing on this side. I have a local max here. We knew we should have a local max since this is a parabola that opens down. So the maximum profit occurs is, let's actually find out what that is. What is P of 4,000? So that's going to be $6,000. Use your calculator to find that. And it requires a production level of 4,000 units. Okay. If we're going to be building a fence, we have limits of material. We also have a particular area that we might want to enclose. A rectangular area is to be enclosed and divided into thirds. Okay, so 1/3, 2/3, 3/3. So like that. We have $800 to spend on fencing material. The outside fence costs $18 per running foot, while the dividers cost $22 per running foot. So I have called this X and this Y, and I should have Y, Y, and Y, but this is actually that I'm bolding is more expensive than everything on the outside. So we have so let's make that let's actually make all this X. There's no reason to divide it like that. X and X and Y and Y. And let's just make this abundantly clear that this is a different material here to us. And that's going to be the stuff that costs more, is what I have in pink there. All right. So our area function is going to be X, Y. That's pretty easy. We'll want to write that in terms of just one variable in a little bit. Our constraints are our $800 budget, our outside fence is $18 per foot. Our dividers that we have in pink are $22 per foot. So how many outside parts do we have? I see that we have 6, 7, 8. So $800 is equal to $18 times all the outside dividers, which is going to be 2x plus 2y plus, and then 22 times 2y. So that means 800 is equal to 36x plus 36y plus 44y is equal to 36x plus 80y. All right. So now we can solve for x or y in this constraint equation. Take your pick. So solve the constraining equation for one of the variables. Then substitute into the objective function. This will reduce the number of independent variables in the objective function, hopefully to 1, because that's what we want. So let's solve for y here. 800 equals 36x plus 80y. 80y equals 36x. Sorry, is equal to 800 minus 36x. And y equals 10 minus 36 over 80x is 10 minus 18 over 40, 9 over 20, like that. So that means that y that means that a is equal to x times y. It's going to be a of x is equal to 10x minus 9 over 20x squared. Let's go ahead and find a prime of x is 10 minus 9/10 x. Going to set that equal to 0. Negative 9/10 x is equal to negative 10. X is equal to negative 10 over 1 times negative 10 over 9 is 100 over 9. X is equal to 11 1/9 feet. I'll leave it as 100 over 9 for a second, just so we don't get any rounding error. Okay. Are we done with the problem? No. What's the problem asking for? The problem is asking for the dimensions, plural, that will maximize the area. So what are the dimensions, plural? Well, we have x, so we know that the width, x, is 100 over 9 feet, which is about 11 which is exactly 11 1/9 feet. Okay, but we need to know our height, y, which is going to be up here. Y was equal to 10 minus 9/20 x. Nines will cancel. 20 goes into 105 times. Y is equal to 10 minus 5 is 5 feet. So our dimensions are going to be 11 1/9 feet by 5 feet. Our maximum area is going to be 500 over 9 square feet, which is equal to 5 is 45 nights square feet. Let's go ahead and ask then, is this within our budget? Let's check. 800 equals 80 times y plus 36 times x, which was 100 over 9. So this is 400. This is 400. And that gets me exactly to my budget of $800. Perfect. So there's my dimensions. So dimensions of 5 feet by 11 1/9 feet maximizes the area at 55 and 5/9 square feet. All right, that's it for this video, and we will come back next time and talk about linear approximations and differentials. See you for the next video.